if you're hearing me clearly. Okay. I want to welcome everyone to my lecture today. We are actually going to continue with the material for, that we started yesterday. We're starting from the change of variable. Okay. Initially, we started at x, and we now have a new variable that is a function of x. So how can we actually find the probability distribution associated with with the new variable y? We've done that for discrete in the deck one slide that we've done before, but now we actually want to repeat the same for continuous random variable. Okay, so because of that, we basically going to get ourselves familiar with what we call invertible functions. So you have invertible, you're actually mapping from x to t using a function g. Now, is that kind of stuff is invertible if you can actually have, you can also map back, like going back from t to x, but only that the function you're going to use this time around will actually be different. And what that means is that if you take a look at this guy here, okay, so the age of g of x now is basically going to be equal to x. We are the support of x is in s, and of course the gh of y going to be equal to y, and where the support of y is actually in t. So I just wanted to take a look at that, and what we're trying to say now is that the h is the inverse of g. Okay, the h is the inverse of g because where the g is mapping forward and the h is mapping backward. It's mapping backward. So I just wanted to take note of that. So h is actually mapping forward, but where g is mapping forward and h is mapping backward. So that is the inverse, and because of that, we can basically write that h equal to g raised to power minus 1. So we can also write that mathematically for that relationship. Okay, so when you are talking about invertible functions, we go talk about the one-dimensional one. You remember the other time when we are trying to find the exponential of something, if I want to go back to the initial value, probably taking the log, okay, because log is the inverse of exponential. I just wanted to take note of that. Okay, and it's just like, take a look at this. I have x and I square that. If I want to go back, of course, I'm actually going to find a square root. Okay, you understand that, right? So that is what, but there's something I wanted to see. Take a look at this. Note that if s to s squared consider as a function on this, okay, because when you square it, okay, there's no negative. If you square, no negative. Okay, don't forget, if you take a look at this here, real number has all negative, has negative, positive. But if your x is a real number, so when you square the result, you're basically going to have will be between 0 and infinity. Okay, and you know what? This is not invertible. Okay, why is it not invertible? In the sense that there's nothing you're going to do here that would, let's say for instance, let me say x equal to minus 3. Okay, when you square x, that will give you 9, right? Okay, now when you find the square root of 9, okay, it's not going to take you back to minus 3. Okay, if you you're just going to have, positive 3. So that's the reason why we say it's not invertible, because y equal to x squared has two solutions. Okay. So, this is what I'm saying. X equal to minus 3. Okay. And you square that, that's going to be minus 3 squared. That would be 9. Now, if I want to find the square root of 9, don't forget there's going to be a plus minus, right? And that is going to be two results, minus 3 and 3, which is different from just minus 3. That's what I'm trying to talk about. Okay. That was why they said that has two solutions. That's why you have minus 3 and 3. Okay. So just take notes. I think a chart came in, and the person said if you define the domain of y and s as this, and would s squared and y be considered invertible? No. I think that is what I just answered now. That is what I just demonstrated. Okay. Here, that was what I demonstrated here. Okay. When you square minus 3, you have 9. Okay. If you find the square root of 9, you're going to have two solutions. That will be minus 3 and 3. So I hope I've cleared that. Okay. Now, I think another shot came in. In this case, where the domain is 0 to infinity. Yeah, the domain, the one that you are actually here, give me 1 second. This one here is the one for s squared. Okay, we're just trying to say, because s squared, there's no room for negative. Okay, so that is what that guy actually means. Okay, but if you take a square root of a number, you're actually going to get two values, and those two values will include negative and positive. I just want to take note of that. So in that situation, the support is not just going to be 0 to infinity. Okay, that is why the two are not invertible. Okay, now the change of variable we really want to talk about here today, like I said, is the one that involves continuous function. Okay, and the idea of Jacobian transformation. Now let me tell you here, we're going to make use of idea of differentiation. We're going to make use of how do we actually find determinant. So the knowledge of calculus and algebra will be used. Okay, now a change of variable process, is kind of different for PDF and PMF. When we're dealing with the PMF for discrete random variable, I think I walked you through that before. But when you're doing it with a continuous function, we got a different way to do that. Okay, suppose we have G, okay, as an invertible function, mapping from X to T. Okay, and you know what? We actually have a subset. Okay, they are actually open subset of days, and H is the inverse of G. I say you know that. We just said that H, YG is mapping forward and H is mapping backward. Okay, so therefore any W, okay, if I consider the integral of W as the S, okay, now the W as the S, you're going to see that in place of X here, it has been replaced by H of Y. Okay, don't forget, why is it replaced by H of Y? Because the H is the inverse of G. Okay, so H of Y is replacing S, okay, then multiply by the determinant of Jacobian. I'm gonna show you how the Jacobian is obtained. Okay, so I'm gonna show you how Jacobian is obtained depending on whether you're dealing with 101 or 2 to 2. Okay, so the G of Y here is what we call the Jacobian matrix. Okay, for the change of variable. Okay, we're always going to have a Jacobian matrix for the change of variable, which I'm actually going to show you. And you know what? That Jacobian matrix have to be a square matrix. That should be a square matrix. Okay, so for instance, if you have two variables to two variables, that would be 2 by 2. If you have 3 variables to 3 variables, that would be 3 by 3. And of course, in each the component, we're basically going to perform a derivative, which I'm actually going to show you. It's very easy. Very, very easy. I cannot show you that. And after that, we can actually find the expected value. Okay. But we can only find the expected value if we have succeeded in deriving, the PDF of the new distribution. Okay. Which I'm actually going to show you. So I'm basically going to say, okay, for instance, if I started with X and the X has a probability distribution, okay, which we call the probability density function, which we actually denote it as PDF, okay, and I define a new variable, okay, which is in terms of X, okay, the original variable, and I'm seeking to get the PDF of a new variable. What I'm going to do is I'm going to plug in h of y, don't forget, which is the inverse of g, into the function. Then I'm going to set up my Jacobian matrix. Then after setting up my Jacobian matrix, I'm basically going to perform some derivative within the Jacobian matrix. Then I'm going to find the determinant of that. Then I'm going to multiply by this. So that's why you have that. So I'm going to demonstrate to you using an example. Now, let's take a look at this. We want to have an example now. Okay, suppose S is an exponential, okay, with parameter lambda, okay, distribution, okay. So if X follow that, now, and if Y is a new variable, which is a function of X, don't forget, X follow exponential distribution. Now, the question now is, what is a PDF of a new variable Y? Okay, now, if you really want to decide that, this guy here, is f of x lambda exponential raised to the power minus lambda x, s greater than 0. Okay, that is a probability distribution of the original variable x. But right now, we're actually seeking to get f of y, which is going to be the PDF of y, where y is actually expressed in terms of the original value of x. Okay, now when you have this guy now, what you're going to do is you rewrite that as this g of x, because it's a function of x, right? Okay, so g of x equal to that. Now when g of x equal to that, you now rewrite your h of y. The h of y is just going to be plug in, instead of you to write x, just write y. Okay, I believe you understand the second step now. Okay, before first start by writing g of x equal to 1 over x, which is, of course, y here is actually g of x, you know that, right? Because y is a function of x. Okay, then the second one, you're going to do hy equal to 1 over y. Now when you do hy equal to 1 over y, you find the derivative. The third line here is the derivative of that function 1 over y. Don't forget here, if you take a look at this, another way to write that is to write it as y raised to the power minus 1. Okay, now when you differentiate that, okay, because what this guy is trying to tell you is g h of y dy. That is what he's telling you, okay, which is equal to this guy now. Look at that. Okay, you've differentiated that. And after differentiating that, you know what you're actually going to do? Now, you're going to go back to the function, which is this guy, the original PDF for x. Then you are now coming to use this formula now. Okay, now what are you going to do? Okay, you first, if you take a look at this, it's like writing this, but in place of x, okay, I wanted to see that guy very well. Okay, you say y equal 1 over x. Okay, what does that imply? X equal 1 over y, right? Look at that. Okay, so what do you think I'm actually doing here? Okay, if you take a look at this guy, okay, instead of lambda exponential raised to the power lambda x, this x now, I'm plugging in 1 over y. Okay, some of you may be wondering, why do I get that? Because that is what is right. It's from here. It's actually from here. Look at that. So you plug in That is why you have this guy. Okay. Then when you have this guy now, then multiply by the absolute value. What did you get from this is the Jacobian now. Okay. Then the Jacobian is the derivative. Okay. That's what you put here. Then what is the absolute value of a negative? It's going to be positive. Then it's just going to be everything here divided by y squared. Then we got this result. Is there anyone who need clarification on how we figure out the PDF of y out? Is there anyone? Now, somebody said, do we always define g of x to be equal to y in such a change of variable problem? Yes, you're gonna do that. Now, somebody said, could you go over how they got Jacobian here? Okay, thank you so much. Actually, the Jacobian is a derivative. Okay, the Jacobian is a derivative. When you replace, this is what you have initially, right? Okay, you're actually going to define a function h where you're going to replace x with y. That was what we did here. Before you can set up your Jacobian, you need to replace that x with y. Okay, and from there you differentiate, and that is what is going to lead to the Jacobian. Okay, the person that chat with me, did the person get it now? Did the person get the explanation now? Okay, like I said, okay, thank you too. Okay, so we got a new distribution in place now. Okay, initially when the PDF is exponential, okay, then the new variable now, the new distribution now is this. So take a look at that. Okay, take a look at that. So that is what we have. But you know what? This is an example of one-to-one, one variable. So one variable, okay, it's like going from x to y. We could have situation where we're going to go from two variables to two variables. In that situation, the Jacobian is going to be a matrix. But right now, Jacobian is not a matrix. Okay, well, I'm still going to walk you through that, the example. Now you can see the new distribution that we actually got. Okay, now I want to tell you the new distribution that we got is looking like an exponent, like a gamma, but I'm still going to talk about that later. But let me go to gamma distribution this time around. Now we have a lot of probability distribution in statistics. We have, I started with, under the continuous probability distribution, I talk about the exponential. So right now, I want to talk about gamma distribution. Okay. The gamma distribution is a very good distribution for modeling waiting time, before the occurrence of an event. Okay. Very useful in survivor analysis and also useful in insurance claims. Now, if you take a look at this now, if first follow gamma distribution, that is exactly what we have. Okay, we have a parameter alpha and lambda. Okay, and the parameter alpha and lambda has to be non-negative, and the brand name of the distribution is this. Do you see that? Anytime you see that, okay, the gamma distribution is abbreviated as that. Now the two parameters that we have, they have their role. Okay, we have the shape parameter alpha, okay, and the rate parameter lambda. The shape parameter is actually responsible for the shape of the distribution. Every probability distribution has a shape. Okay, you know what I mean by shape, the way it is distributed. Okay, whether it is skewed or it is evenly distributed. So that alpha is what actually, under the shape, and why the rate is the lambda. Okay, I just wanted to take note of that. Now, what if in a situation, take a look at this now. You have a distribution given as gamma. Okay, I think a chart came in. Oh, okay. The person said yes, thanks. Now, and we want to see whether the density actually integrate to 1, because we have for a valid PDF, we expect that the area under a curve should be equal to 1. Okay, now if you want to do that, we can actually assume that y equal to lambda x, because you can see the exponential carrying the lambda and x, right? So when I do y equal to lambda x using what I call the substitution method, okay, you basically, from here, okay, what is your x? Your s is going to be equal to what now? Your s is going to be equal to y over lambda. And you can no longer have a ds. Okay, so what is the y ds from here? Okay, the y ds is basically lambda when you differentiate. And what is going to be your ds now? Okay, so your ds is basically going to be the y over lambda. Okay, and that is the reason why here I'm plugging in the y over lambda for that. Okay, and then for x, what am I plugging in? Y over lambda. Look at that. And then, the lambda s is just y. Do you see that now? Okay, so that is how we actually arrive at that. So here now, you just need to simplify. Okay, if I want to simplify, okay, you basically, if I want to, let me rewrite that so that you will understand what I mean. Okay, so if you take a look at this now, so get a lambda raised to the power that gamma alpha, okay, is 0 to infinity, y raised to the power alpha minus 1, okay, divided by lambda raised to the power alpha minus 1, exponential raised to the power this, the y, divided by lambda. Okay, now when you take a look at this guy and this guy, that would be lambda raised to the power alpha if you combine them. And that will cancel this guy here. They will all cancel out. Okay, when they cancel out, what do you have? That's a gamma function, right? You remember what I walked you through the other time. That's a gamma function. That's a gamma alpha. Okay, which is the same thing as this guy here. It's going to cancel that. Okay, which is basically going to give you 1. Okay, and when you have 1, what does that mean? It actually means that probability distribution, that we call the gamma distribution, is actually, a valid one. Okay, it's actually a valid one. Okay, so that is how to show that, and you know what? When alpha equal to 1, if I come here now, I plug in alpha to be 1. Let's see what we're going to get. Okay, so alpha equal to 1. Okay, that will be raised to the power 0, x raised to the power 1 minus 1. Okay, this. Okay, gamma 1. So this is going to be 1, 1, 1. What do I have? I got exponential raised to the power that. Okay, which is more or less like it's still an exponential function, if you take a look at what I have. So, which means when alpha equal to 1, okay, the gamma distribution will actually take us back to exponential. That's what we mean, okay? So, which means the gamma of 1 comma lambda equal to that. So, don't forget your alpha here is 1, okay? So, therefore, exponential distribution is a special form of a gamma distribution. I'm going to say that again. Exponential distribution is a special form of a gamma distribution. Exponential distribution actually goes without bounds. It's just like you have a constant hazard. The rate of hazard is constant over time, which may not be true all the time. Okay, and that is the reason why we need alpha in the distribution that we call a gamma that is going to tell you the hazard rate is not, is not constant over time. Okay, so that is exactly what I actually mean here. So exponential is a special form of a gamma distribution, and we got exponential distribution when alpha equal to 1 in a gamma distribution. And don't forget the alpha represents the shape. Okay, so I just wanted to take note of that. Now, the next thing we want to do now, I want to show you a situation whereby we can have a 2 by 2, and the change of variable. I'll just walk you through 1 by 1 to 1, where s is distributed as exponential, and we define a new variable, which is 1 over x. of the original variable, and you saw what we derive out. But right now, we basically want to consider a situation, suppose, we've already defined our gamma distribution, and let's say we have two independent gamma, like for instance, X follow gamma distribution with parameter alpha 1 and lambda, and Y follow gamma distribution with parameter alpha 2 and lambda. And if you take a look at the X and Y, they are independent, but only that they have the same rate parameter, but they have different shapes. We know the different shape they have is the alpha 1 here, alpha 2 here. They are not the same. You get what I mean? Okay. Now we want to define a new set of variable. Okay. We want to define new set of variable. We are, for instance, what is the distribution of U? Okay, where U is going to be the addition of the two. Okay. And of course, the idea of convolution can be used in a situation where you are actually seeking the probability distribution of the sum. I walk you through the convolution the other time. But what of in a situation where we actually want to consider a new variable V, and that very new variable V is a function of X and Y. Okay, so which means we can actually define a new distribution for for V. Maybe what we're looking for, this is what we're looking for, but we cannot go from X and Y to just V. We can't go from two variable to one variable. We can only go from 2 to 2. We can go from 1 to 1, 2 to 2, 3 to 3. Now, because of that, we can actually create what I call an artificial variable. Okay, for instance, I'm seeking to get this guy here. Okay, give me 1 second. Okay, so probably I'm seeking to get this guy. I'm seeking to get a new variable V. Okay, but I actually create an artificial variable U. Okay, because why am I doing that? Because I can't go from two variables X and Y to just V. I can only go from two variables X and Y to another two set of variables. And at the end of the day, I'm actually going to integrate out the artificial one that I created, which is this guy here. Okay, I just wanted to take note of that. Now, this is the situation by convolution. Okay, if X follow gamma and Y follow gamma, okay, at the end of the day, okay, the U is basically going to also follow gamma distribution, only that we're going to have the addition of alpha 1, the shape parameter. They're still going to have the new distribution is still going to have, the same lambda, the rate parameter. Okay, you can try that using convolution. For those of you who try that, you can send that to me. I've walked you through convolution, right? Okay, you remember we did a convolution. Okay, with the convolution, okay, the idea of convolution can be used when you define two variables that follow distributions, and you're actually seeking to get the probability distribution associated with the sum of them. Okay, so convolution can be used to get that. But the major thing is, how do we get the new distribution for V? Okay, so which I'm actually going to walk you through. So now I wanted to sit back now. Okay, we want to get, let me tell you this. If you want to, this is the way the question will be asked. They're going to give you something like this only in the question. And they will only ask you this question. They're going to say, given that, so find the PDF of V. You are not going to be giving this guy here. Okay, you are not going to be giving that. You will be the one that will think about that. You will be the one that will think about getting an artificial variable U. But most of the time, situation where you are actually seeking for ratio, the artificial variable U is going to be a denominator. It's going to be a denominator to the new variable you are seeking. I just wanted to take note of that. Like I said, you are not going to be giving this guy. They're only going to give you this. Okay. And since you know you cannot go from two variable to one variable v, you needed to create an artificial variable u. And that very u is basically going to be the denominator. Please take note, x plus y. That's why you have it here. Okay. Now you understand how I figured out how. Okay. Then I'm going to go back into how to do that now using the method of Jacobian transformation. Okay. Now, if you want to start, don't forget, this is what you're seeking, right? And this is the one you create. This is an artificial one. Okay. This is artificially fabricated. Okay. You artificially fabricated. Okay. This is a real one. Okay. Now, after that, you have this in place. Now, what you're actually going to do now is, if you take a look at this, u and v, they are in terms of x and y, right? The very first thing you need to do, express x and y in terms of u and v. Express x and y in terms of u and v. Okay. Now, you were initially in x and y. The x and y are the original variables. You are moving to a new set of variables called u and v, though the expression you were given initially is expressing the new variable u and v in terms of x and y. If you want to start, what you need to do, you need to express x and y in terms of u and v. That's exactly how we find this. Okay, what have we just done? We express x and y in terms of u and v. Okay, so that's exactly what we did now. Okay, so if you take a look at so when you go through all this, you're basically going to arrive at that. Okay, we just express that in terms of that. Okay, now after that, what is going to be the next thing? Because I need this to set up my Jacobian matrix. Okay, I need that to set up my Jacobian matrix. Okay, like if I want to set up my Jacobian matrix now, okay, I need the x. Okay, so if the s, the v, the s, the u, then I'm going to come back to the second one. I need the y, the v, then the y, the u. Now see, u, v, v. Okay, take note. And y, x, x. Look at that. Okay, so because I have two sets of equations, I'm actually going to have 2 by 2 Jacobian matrix. If I have 3 sets of equations, I'm going to have 3 by 3 Jacobian matrix. Okay, now after that, that was how I came here. Look at that. Easy now. That is based on this. Look at that. Step 1, you express u and v. You express x and y in terms of u and v. Don't forget, originally u and v was they were expressed in terms of x and y. Okay, it is after you have succeeded in expressing x and y in terms of u and v that you can actually set up your Jacobian matrix. Your Jacobian matrix now. Okay, somebody say I'm a bit confused how you came up with give me 1 second. How you came up with u and v. Is it arbitrarily what you define then? Okay, the u and v, you were actually, okay, I'm going to go back. You were actually given in the question. I'm going to go back. Like I said, the question is going to come this way. And they're going to ask you to find this. They're going to give you this, and they're going to say, find PDF of Y. PDF of V. They're going to say, find PDF of V. The person that sat with me, I think you get that. You're going to be given this, the one I circle now. You are not going to be giving you. You will be the one that will create you. Okay? And how are you going to create you? U is going to be the denominator of V. Does that make sense? denominator of V. Okay. Okay, it's making sense to you now. Okay, now let me go back to what I was doing. Now, we're already at this is like step 1. Okay. Now, setting up the Jacobian now is step 2. If your step 1 is wrong, your step 2 is going to be wrong. Please take note. If your step 1 is wrong, your step 2 will be wrong. Don't forget, your step 1 is, okay, the two variables that you're giving express X and Y in terms of the new variable. The X and Y are the old variables. Okay. Now you're going to come to the Jacobian now. Jacobian is going to be in terms of U and V, where you want to differentiate X with respect to U and differentiate the same X with respect to V. Then you come back to equation 2. Okay. Somebody said, how do we, give me 1 second, how do we decide that J is arranged that way? How should we decide for 3 by 3? Okay, that's a good question. If you take a look at this, X, X, Y, Y. Look at that. If you want to go by row, that is X. You are doing a partial derivative. If you take a look at this, you have U and V. You differentiated that with respect to U first. Then the second one is going to be the respect to V. You're also going to maintain the same thing in the second row. Look at the second row. Because in the second row, you are making use of the second equation, Y. You differentiated Y with respect to U first. Then the second row, you differentiated that with respect to V. I don't know if that is clear to you now. Okay, now, here now, differentiating X with respect to U, that's going to be V. Because this is what we call partial derivative. Partial derivative. When you are differentiating with respect to one variable, the other variable will be kept at constant. Okay? When I differentiated here with respect to U, then V is a constant. Okay? Now that is why you have this now. When I differentiated with respect to V, U, I got U, look at that. Then coming here now, you do the same. I will advise that if you want to differentiate here, 440 U minus UV. Okay, now differentiate this guy now. With respect to U, it's going to be 1 minus V. Then with respect to V, it's going to be minus U. Look at that. Is there anyone who have trouble time on how I got all this? We're making use of this guy here, using the idea. I don't know whether you've heard about multivariate calculus. Okay, this is more or less a multivariate calculus. Very easy. Is there anyone who have a trouble time with that? Okay, so in the second step now, you set up your Jacobian matrix. What am I going to do now here? I'm going to find the determinant. What is the determinant? This multiplied by that. This multiplied by that. Then I'm going to subtract. That's what I'm going to do next. Super easy, right? So you're going to see minus UV minus U into 1 minus V. Okay, so I'm going to do the determinant. So what am I doing? It's like I'm doing the determinant. Okay, you remember determinant in algebra for 2 by 2? When you set up your matrix for 2 by 2, you're going to multiply it across, then you subtract. That is exactly what you're going to do next. Okay, that is what you're going to do next, which is what I did here. I find a determinant, and that actually gave me, when you simplify, like here now, minus UV minus U plus UV. This cancel this. I got a minus U. That's how I got that. Look at that. Okay. Is there anyone who doesn't understand how to figure that out? It's super easy, right? You find the determinant of 2 by 2. And after finding the determinant, what are you going to do next? We're now going to go back. I want you to follow this squarely now. Okay. You're going to go back into the PDF original function. Okay. When we're told that x1 and x2, okay, are independent. Okay, we know that x1 and x2 are independent, right? Okay, so if x1 and x2 are independent, okay, what we actually going to have, okay, is what is the f of x and y? You remember, I need to have f of x multiplied by f of y. Why? Because x and y are independent, right? Okay, now if x follow gamma, okay, and y follow gamma, okay, what we actually going to do first, don't forget, you were told here, let's go back to the question. Okay, look at this. Okay, x follow gamma, y follow gamma. Okay, now, and what is the expression for gamma? I'm going to take you back to the expression for gamma so that you understand what I mean. Okay, this is the expression for gamma. Okay, you know what I'm going to do now? I'm going to make use of my whiteboard. Okay, I'm going to make use of my whiteboard so that you will be able to understand what I mean. Now, give me 1 second. I'm going to stop my share. Okay, because I'm in a very critical stage now, which I want everyone to really understand. Give me 1 second. I'm going to share my whiteboard. Okay, I need you to confirm if you definitely see my whiteboard. You all see my whiteboard? Okay, thank you so much. We've done up to step 3, right? Where we've already derived the determinant, we've obtained the determinant of Jacobian. The next thing we're going to do now, we're going to go back to, we're told that x1 follow gam, okay, with parameter alpha 1, lambda. Now, what is f of, give me 1 second. Oh, if x follow, we're told that x follow that, right? What is now going to be f of x? Now we need to write that out. Okay, it is lambda raised to power alpha 1, then gamma that, then x raised to power alpha 1 minus 1 exponential raised to power lambda x. Okay, that is f of x. Now, we also told y follow gam, okay, a parameter alpha 2 lambda, then you're going to write that f of y equal lambda raised to power alpha 2 now, gamma alpha 2, okay, y alpha 2 minus 1 exponential raised to power lambda y. Do you see that now? You need to first write this out. Okay, now you were told that x and y are independent, right? If x and y are independent, it means we need the joints of that. F of xy is going to be the product, right, of this multiply by that. Then it means I'm actually going to multiply this guy by this guy. Okay, so now I need to get a joint now. So getting the joint, okay, so lambda alpha 1, okay, another lambda alpha 2, okay, divided by gamma alpha 1, gamma alpha 2, okay, x raised to the power alpha 1 minus 1, then y raised to the power alpha 2 minus 1, exponential lambda s, exponential lambda y. Do you all see that now? What have I done? Okay, I'm using the idea that they said x and y are independent. You can take a screenshot. So take a screenshot, you can take a screenshot now, okay? Take it. Okay, now I've just got the product now. Okay, now when I got a product now, okay, what am I gonna do next? What I'm gonna do next now, okay, I can bring this guy together, right? Law of indices, right? I can also bring this guy together, okay? Law of indices, if you want to look at the exponent. If I want to rewrite this guy now, okay, I'm just gonna write, I can write lambda raised to power alpha 1 plus alpha 2. You know that? And if I want to do this guy now, okay, I'm gonna have I can rewrite that as x plus y. Look at that. Okay, now take a look at this. That's a joint, right? Okay, this step 4 now is writing the joint. Now, after writing the joint, what am I going to do? What I'm going to do after writing the joint now, okay, I'm going to go back to my equation, okay, and I'm going to start plugging in anywhere I see x and y. I'm going to plug in, take a look at it. What is x plus y? Don't forget, x plus y is u. You remember? X plus y is u. You remember? Right? Okay. So I'm going to plug in u here. Okay. So I'm going to replace x and y. Okay. We have already derived a function for that. Now, because of that, I'm actually going to go back and I'm going to go back to material now. Okay. What I'm just going to be doing now, okay, I'm actually going to plug in x and y, okay, which is going to be in terms of u and v. Okay. That is what you're going to see me doing. Okay. Then I'm not going to multiply by determinant of Jacobian. Now, take a look at this. Look at what I want to do here now. I've already gotten x and y. I've gotten f of x and y. And now I'm seeking to get f of u and v. And getting f of u and v, what am I going to do? Where I see x and y, I'm going to be plugging value. Look at that. This is supposed to be x. I put that. Supposed to be y. I put that. Then multiply by determinant of Jacobian. I'm going to show you again. Let's go back. What do we derive for x? Look at that. S is uv, right? Y is what? U into 1 minus v, right? Okay, the joint that I showed you the other time, anywhere you see x, plug uv. Anywhere you see y, plug u into 1 minus v, okay? When you plug in that, you are no longer having f of xy, but you are having f of uv. That is why you have the, look at that. We're plugging in that into that, then multiply by the determinant of Jacobian. Okay? That is exactly what we're doing now. We move from f of xy to f of uv. And what do? We just, anywhere we see x, we put uv. Anywhere we see y, we put this guy here. And at the end of the day, we multiply by determinant of Jacobian. Don't forget, the Jacobian that we got was minus, right? Okay. What is the absolute value of that? Don't forget, you're going to do absolute value of determinant of Jacobian. Okay. So which is going to be absolute value of that, which is going to be u. Okay. And that is what you have here. That is what you have here. Now, every other thing now in the product is now in terms of u and v. You see that now? That is in terms of u and v. I'm going to spend additional 5 minutes on this so that you'll be able to understand more. Okay, so that will lead to this guy here. And you just need to simplify. When you simplify, you're actually going to end up here. But you know what? This guy here is just f of uv. But can somebody tell me, what am I looking for? I'm looking for f of v. How do I get f? Can somebody tell me for extra credits? What do you think I'm going to do if I want to get the f of v from f of uv? Can somebody tell me, what am I going to do for extra credit? This is a function of u and v now. That's a joint, u and v. But this is what I'm looking for. I'm looking for marginal f of v. What am I going to do? Can somebody tell me? For extra credit, if I want to get f of v from f of uv, what are we going to do? Okay, what you're going to do is this. And somebody said, do the integral of the function over u. That person should send a message to me for extra credit. You are fantastic. Good job. Okay, I'm good. I'm looking for f of u. Then I'm going to integrate f of uv. Okay, with the respect to the, with the respect, if I'm looking for f of v now, then with the respect to u, you are very correct. Now, what I'm going to do next now, after I've gotten this f of uv, okay, what I need now is to integrate this with respect to u. Don't forget I told you, we did not need u initially. That was artificially fabricated. We're going to integrate it out. Okay, now I'm going to share my screen now. Please pay attention to this. I'm going to share I'm going to stop sharing, and I'm going to show you how you're going to do it. Very interesting. You're going to see now. Now I'm going to write, okay, I'm going to write f of uv is equal lambda alpha 1 plus alpha 2 divided by gamma alpha 1 gamma alpha 2, okay, u raised to power alpha 1 plus alpha 2 minus 1, then v raised to power alpha 1 minus 1, and 1 minus v raised to power alpha 2 minus 1. Now, you know what we want to do now? We want to find f of v, okay? And we said we need to integrate that f of uv with respect to u that we are not interested in. Don't forget, what is going to be the range of u? Don't forget, if x follow gamma, x, the support of s is from 0 to infinity. And the support of y is also from 0 to infinity. And don't forget, u is x plus y. It's also going to be from 0 to infinity. So what I'm going to do now, so I'm going to write integral 0 to infinity, lambda raised to power this, gamma alpha 1, gamma alpha 2, give me 1 second, gamma alpha 2, u raised to power alpha 1 plus alpha 2 minus 1, v raised to power this, and 1 minus v raised to power alpha 2 minus 1 du. Okay, so take a look at that now. Du. Now, when you are integrating with respect to u, anything v is going to come out of the integral, anything that is not u. So I'm going to have v raised to power alpha 1 minus 1, 1 minus v raised to power alpha 2 minus 1, okay? And all this guy here, they're also going to come out, okay? They're going to come out. So it's like I'm actually going to have this divided by this divided by this, and lambda raised to power alpha 1 plus alpha 2. What am I only going to have inside the integral now? It's just going to be this guy, u raised to power alpha 1 plus alpha 2 minus 1 du. This is the only one I'm going to have inside the integral. Take a look at that. I think there's another thing that is missing now, which is going to be exponential. I think I didn't copy that completely. That was one. Give me 1 second. Let me stop. I'm going to stop my share now. There was one expression that is actually missing now. Okay, so the expression that is missing now is this guy here. Exponential is power minus lambda u. You see that, right? Okay, so I'm going to copy that back. Exponential is power minus lambda u. Okay, so let me see if I can have a way to. Okay, now this is what happened. This is what I actually, like I said, I'm gonna make sure I explain that. Okay, so we actually want to find the f of v, okay, so which is said is 0 to infinity. And before that, I think we've already written this guy out. We've written lambda raised to power alpha 1 plus alpha 2 divided by gamma alpha 1 gamma alpha 2, okay, and we've already also copied this guy out, v raised to power alpha 1 minus 1, 1 minus v raised to power alpha 2 minus 1, and we've copied all those guys out, okay, and what we have inside the integral sign, we have exponential raised to power u, was it lambda u, is that what we have? I think it was lambda u, right? Then we actually have after that one, then we have u raised to power alpha 1 plus alpha 2 minus 1 du. Okay, so that was what we actually have. Okay, so take a look at that. Okay, so that was what I think I'm going to check very well. Okay, exponential is power minus lambda u. Okay, that was what we have. Okay, now when you have this guy now, let's concentrate on this. By using a substitution approach, let m be equal to lambda u, right? Okay, u is going to be what? U is going to be m over lambda, right? Then what is the m du? The m du here is going to be lambda. And what is the u? The u is going to be the m over lambda, right? Okay, now, if I want to write the whole thing, I know that, let me keep this for now. That's a constant, right? So let me concentrate on the one in the integral sign. So 0 to infinity, exponential raised to the power minus m. So instead of u, m over lambda raised to the power alpha 1 plus alpha 2 minus 1. Instead of the u, the m over lambda. So take a look at that. Now, if I have that now, you're basically going to see here, okay, that I'm going to have 0 to infinity exponential raised to the power this. I'm basically going to have m raised to the power alpha 1 plus alpha 2 minus 1, okay, and the m, and I'm basically going to have lambda, lambda carry alpha 1 plus alpha 2. Instead of minus 1, it's going to cancel that guy out. I'm basically going to have that guy. So if you take a look at this now, you're going to see that this will cancel this, right? Okay. And if that actually cancel, you know what we have in the integral sign now. Okay, let me rewrite the new thing that we have in the integral sign now. So in the integral sign, we only have exponential raised to the power this, m raised to the power alpha 1 plus alpha 2 minus 1 dm. Now, that is what we have left now. So if I clean up now, what do I now have? Using the gamma function now, can somebody tell me what this guy is going to be? The one in the integral sign. Using the gamma function, that will be gamma what? If you really want to get that, that will be gamma 1. So let me write what I have now. I have this one here, 1 minus v raised to the power this, divided by gamma alpha 1, gamma alpha 2. So what do I have? Using the gamma function, the one in the integral. Can somebody tell me what I'm going to have for this? What is it? What am I going to call that? What gamma is that? When I have exponential carry negative m and m raised to the power alpha 1 plus alpha 2 minus 1 dm, what is it going to be called? Take a look at that. That is gamma alpha 1 plus alpha 2. If you use the idea of gamma function, that is gamma alpha 1 plus alpha 2. Okay? That is exactly what you're going to get. If you take a look at this new distribution now that we got, this is called a beta distribution. Beta distribution of the first kind. That's a new distribution that we just derived. Okay? That is a new distribution that we just derived. Do you know the exercise that I want to give you now? When I find the marginal distribution of f of v, this is what it gives. I want you to also find the marginal distribution of f of u. F of u. And I want to see what you're going to get. I'm going to say that again. Find the marginal distribution of f of u. Make use of the joint of u and v. I make use of the joint function of u and v, right? And I find the marginal distribution of v. That is how I arrive at this. I also wanted to use the marginal distribution of u, that f of u. And you're basically going to see, but I'm going to tell you, it will lead you to gamma distribution of where the parameter is going to be alpha 1 plus alpha 2 comma lambda. I just wanted to try that. Okay, I'm going to stop here today, and I've decided, finally, I'm going to make announcements about that. Okay, I've decided to skip assignment for this week. I'm gonna say this again. I have decided to skip assignments for this week. Because if I decided to release assignments yesterday on Tuesday, of course, I'm actually going to disrupt your pattern. Some of you work. So I want the assignment to return back to traditional Sunday to Sunday. Okay? And I don't want to disrupt the plan. So because of that, assignments is for this week is put on hold. Okay? All what you just need to do is take your time, spend a lot of time, okay, on this, on the, right now, you're moving rigorously now to mathematical, you're moving towards a mathematical complexity now, where we make use of, we differentiate, we integrate, we do some algebra, so like I said, you're going to receive an announcement on that assignment for this week is canceled. Because if I release assignment yesterday, I'm going to disrupt your regular plan for Sunday to Sunday. But I want to, instead of you doing assignment, I think this is what you can do. I think I've given you an exercise now. Find the f of u. Show me clearly from the joint. Let me just revisit what I've done today, particularly the area of moving from two variables to two variables. You were given x and y that follow gamma distribution. Okay, x follow gamma distribution with parameter alpha 1 and lambda, and y follow gamma distribution with parameter alpha 2 and lambda. And of course, you are seeking to get a probability distribution for y, where y equal x over x plus y. That is what you are seeking to get. But I say you're going to create an artificial variable because you cannot move from two variables to one variable. You can only move from 2 to 2. And that's why you created artificial variable u. The u that you are creating has to be a denominator to the one you are seeking, which is x plus y. And the very first step that you actually need to do is to express x and y in terms of u and v. That is the first step. And after expressing x and y in terms of u and v, the next thing is to set up your Jacobian matrix. And setting up your Jacobian matrix, then the next thing is perform the derivative inside that. Then from there, where you find the determinant of that. And when you find the determinant, don't forget you're going to find the absolute value of your determinant. In case you get a negative, you're going to have a positive. And after that, the next thing you're basically going to do is to go back to the original distribution. X follow gamma with parameter alpha 1, lambda, and y follow gamma with parameter alpha 2, lambda. And since they claim that x and y are independent, then you can write the probability of the joints, which is going to be equal to the product of the marginal. You write it out. And after that, that would be your f of xy. Now from f of xy, you want to get f of uv, which is the joint distribution for u and v. The only way you can get the joint distribution for u and v is to first get the joint distribution for x and y. Now, when you get the joint distribution for x and y, if you want to get the joint distribution for u and v, you're going to substitute. You're going to substitute for x and y. Don't forget, you've already expressed x and y in terms of u and v. Then after doing that, then you multiply by the determinant of Jacobian. That will give you the f of uv, which is going to be the joint. But that is not where you are going. Okay, where you are actually going now that you have the f of uv, you now need to find the marginal distribution of f of v. Don't forget, that's what you're seeking. And for you to get the the marginal distribution of f of v, you're actually going to integrate f of uv with respect to the variable you are not interested in, which is basically going to be with respect to u. Okay, and when you do that, you get your f of v. And a question can also be asked to get the f of u. If you want to get the f of u, then you can actually integrate the joint of f of uv over the range of v. With that, you get it. That is the way to get it. Just as easy as that. Okay, I want to thank everyone who have attended my lecture today. I'm sorry I needed to spend an extended time because of the calculus nature and the algebraic nature, because I need to explain that very well. So like I said, there's not going to be assignment this week. Spend your time on what we've done before. I don't want to distort your plan like you are used to Sunday. And you know the reason why I did not actually release assignment on Sunday, because I don't want to ruin your independence holiday. Okay, so take your time. Okay, so when I stop this session now, I'm going to start my office hour immediately in case somebody want to meet with me. Make sure you stay safe and have a lovely day. So bye for now, everyone. Thank you too. You're welcome. Yeah, thank you.